Welcome back to the gretl Instructional Video Series. In this video, we will be learning how to use gretl to identify and estimate an ARIMA model. The only file that you will need to follow along with this video is called ARIMA. The 4 items covered in this video follow the 4 steps to identifying an ARIMA PDQ model. First, we will determine D by using the ADF unit root test. Second, we will determine P and Q using the ACF and the PACF. Third, we will estimate the ARIMA model. And fourth, we will create forecasts for the holdout period. Now let's open gretl and get started by opening the data series ARIMA. To open the dataset, click on File from the main menu, followed by Open Data and then User File. Now locate the file ARIMA. Once you have located the file, double-click on it to open. In this case, there is only one variable called V1, and it contains weekly data from January 1st of 2003 through January 26th of 2011. We are going to restrict the sample from January 1st of 2003 through December 29th of 2010. After identifying the ARIMA model, we will use it to forecast the first 4 weeks in 2011, and we'll compare the forecast to the actual values from the holdout period. To restrict the sample so that it excludes the holdout period, select Sample from the main menu, followed by Set Range. In the window that pops up, keep the start date at January 1st of 2003, but change the end date to December 29th of 2010. There are 418 observations in the restricted sample. Now, let's move on to the first step in identifying the ARIMA model. The first step to identifying the ARIMA model is to determine the order of integration, which is the letter D. D is equal to 0 if the time series does not need to be differenced to make it stationary. D is equal to 1 if it needs to be differenced 1 time to make it stationary. We will use both a time series plot and the augmented Dickey-Fuller unit root test, abbreviated ADF unit root test, to determine the order of integration. Now, let's go back to the gretl main screen to create a time series plot. The quickest way to make a time series plot from the main gretl screen is to right-click on the variable and then select Time Series Plot. Once the time series plot opens, you will notice that the data appears to have a constant mean and a constant variance, so you might want to guess that D is equal to 0. We are going to perform an ADF unit root test to confirm this. The null hypothesis for an ADF unit root test is that the series contains a unit root, against the alternative that the series does not contain a unit root. In this case, we expect to reject the null hypothesis because the series appears to be stationary around a constant. If we reject the null hypothesis, then D is equal to 0 because the data series does not need to be differenced to be made stationary. Now let's go to the main gretl screen to perform the ADF unit root test. To perform the ADF unit root test, click on the variable V1 so that it is highlighted in blue. Next, select Variable from the main menu, followed by Unit Root Tests and Augmented Dickey-Fuller Test. There are several boxes to fill in before running the test. First, we need to determine the maximum lag order. It is common to select the maximum lag order using the cube root of the sample size. The cube root of 418 is 7.47. I always round up just to make sure to include enough lags, so let's select a lag order for the ADF test of 8. Next, we want to check the box Test Down for maximum lag order. This means that gretl will start with 8 lags and test down using a 10% significance level to determine the number of lags to include in the ADF unit root test. Now we need to decide whether or not to check the remaining boxes. We will use the time series plot to help us decide. We know that the mean of the series is not 0, so we will not check Test Without Constant, but we will check Test with Constant. The time series plot did not exhibit a trend, so we will not check the next 2 boxes. Also, do not check Include Seasonal Dummies or Show Regression Results. Lastly, select Use Level of Variable. Now we are ready to click OK, and the results will open in a new window. The p-value is located at the bottom of the output. It is equal to 0.0001, so we reject the null hypothesis of a unit root. This means that the data does not have to be difference to be made stationary, so D in the ARIMA PDQ model is equal to 0. Next, we are going to determine P and Q. To determine P and Q, we need to plot the correlogram and visually inspect the patterns in the ACF and the PACF. This takes practice and is not as straightforward as selecting D. Now let's go back to the main gretl screen and create the correlogram. To create the correlogram, click on the variable v1 so that it is highlighted in blue, and then select Variable from the menu, followed by correlogram. Let's use a maximum leg of 30, so input 30 into the window that pops up. After clicking OK, open the graphical output. At first glance, both the ACF and the PACF contain a pattern. The ACF is decaying and the PACF is also decaying, but with an oscillating pattern. These patterns point to both P and Q being equal to 1. We have now determined that P and Q are equal to 1. Since we have already determined that D is equal to 0, we have an ARIMA 101 model, which is also called an ARMA 11 model. Now we are ready to estimate the ARIMA model. After estimating the ARIMA model, we are going to forecast the first 4 weeks of 2011. To estimate the ARIMA model, go back to the main gretl screen. On the main gretl screen, select Model from the main menu, followed by Time Series, and then ARIMA. Now, select V1 as a dependent variable. Next, select an AR and an MA order of 1, because we found both P and Q to equal 1 from the ACF and the PACF. Select a difference of 0, because we found D is equal to 0. Now, leave the remaining options as the default values. Once you have filled in each of the boxes, click OK. We are now going to discuss the coefficients and the p-values from the ARIMA output. The first coefficient estimate is for the constant, which is equal to 17.35 and is statistically significant. The second coefficient is equal to 0.83 and it represents the AR component. It is statistically significant as well. The third coefficient is equal to 0.67 and represents the MA component. It is also statistically significant. Now we are ready to forecast the ARIMA model. We are going to use the ARIMA model identified using observations from January of 2003 through January of 2010 to create forecasts for the first 4 weeks of 2011. Since we already know the actual values for the first weeks of 2011, we can check the accuracy of the ARIMA forecasts. To create the forecasts, open the output from the ARIMA estimation. To forecast the series, select Analysis from the menu, followed by Forecasts. The start and end point already indicate that the forecasts are for January 5th through January 26th of 2011. We will use the automatic forecast, which is a dynamic forecast. Let's include 1 year or 52 pre-forecast observations in the graph. Plot the 95% confidence interval using error bars. When you click OK, the forecast will open in a numerical and a graphical form. Let's look at the graphical form. The red line represents the actual value, while the blue line represents the forecasts. The last 4 observations are the forecasts for our holdout period. You will notice that the green error bars increase with each forecast. Now, let's look at the numerical output. If you scroll down to the bottom of the output, you will see the forecasted values for the first 4 weeks in January. Below that are the forecast evaluation statistics. Other than the root mean squared error, you have discussed the first 7 measures in class. Lower values of these measures mean better forecast accuracy. Before moving on to the key points to remember, I want to point out one more thing about the forecasts. We had the option to pick dynamic or static forecasts. If you select dynamic forecasts, as we did, the forecasts are based on the previously forecasted value. If you select static forecasts, the forecasts are based on the actual rather than the forecasted value. This method is useful if the actual data for this week is already available when you are forecasting the value for next week. The static method is also called the one step ahead or the rolling forecast. Now, let's wrap up the video with 3 key points to remember. The first key point to remember is that the ADF unit root test can be used to determine D in the ARIMA PDQ model. The second is that the ACF and the PACF can be used to select P and Q in the ARIMA PDQ model. And third, selecting P and Q takes experience and practice. This concludes the 6th video of the gretl Instructional Video Series.